Hello, my name is Noel D'Souza, and this is my video report for Lab 2 for Physics 2211. So the purpose of this lab was to observe the motion of a real object or a projectile that was thrown, and then analyze the position of the object and build a computational model to represent this motion. So I decided to do this by recording a video of a crumpled up piece of paper that was thrown, and then analyzing that paper and the motion of it. So here is the video of the paper being thrown. You can see that we have a meter stick that is measuring or used as like a kind of a base measurement to know what a meter is. And then you can see that the paper gets thrown. So here is me putting the video into the tracker, and I went through and I clicked on every single frame where the ball was to get an accurate representation of its changing position over the course of the video. So I used 20 frames for this. You can see that the tracker video is on the left over there, and on the right it has the data points, the time, and the graph of where the projectile is moving. So here's the code, or sorry, the loop of the code that is like actually updating the position of the computational model. So before I adjusted the set like initial position, initial velocity, mass values to be for like my instance. But this is the loop where it's actually calculating everything. So first it calculates the force of gravity, the speed, which is just the magnitude of the given velocity, and then the drag. At first, the drag we set to 0 to see what would happen just with gravity. And then in the second graph, we look at what would happen if drag is included. Then you calculate net force by just adding together the force of gravity and force of drag. Update the ball's velocity, update the ball's position based on the values I previously inputted, update the time, and then basically it's just plotting and giving that like giving that animated representation of what the ball's doing. And then it's just going to print the position so I can take that data and put it later into Excel to compare against the actual data. So here is the graph of the trajectory of the object without drag. So this is when I set that b equal to 0, so it just doesn't count the drag force. And you can see what happens to the object just when gravity is affecting. And here is the graph of the output of here is the graph of the object's position trajectory with drag. So this is when I set that b. I set it to a really low value, but it still affected the position of the object from the computational model. And here's the final result. So I took the actual graph, which is the blue dots, the x graph. Then I took the gravity and the drag, which I calculated which I got from the computational model. And you can see that they're super similar because I set the drag to a really low value. But yeah, so both of the graphs are pretty similar, and they both pretty well represent the actual motion of the object, which I got from the tracker. Okay, and to answer the two post-lab questions, no, this lab does not show terminal velocity because it is not traveling for long enough. An experiment that could show terminal velocity would be dropping an object off of the top of Carlsland. And if you throw the object straight up, it would take longer. Because it has the same speed and is thrown straight up, all of the force is going to be in the upward direction, the y direction. So if you look at the equation derived for time, you can see that it's just the velocity over gravity. And because the upward velocity is going to be greater than the other velocity, it's going to take more time. And finally, some limitations. So, of course, there is human error. I could have clicked wrong in the tracker. Or there's also the frame rate. So, the frame rate doesn't perfectly capture the motion of the object. And then also, this is 2D motion based on the video when in reality it was 3D. And also, this doesn't account for all the factors. But yeah, this has been my video presentation for Lab 2. Thank you so much for watching.